What kind of bond will form? So let's begin by talking about electronegativity. Electronegativity is how strongly an atom is going to attract electrons that are being shared in a chemical bond. So it's sort of like there's a tug of war going on here for those electrons that are being shared in a bond between two atoms. And whichever atom is more electronegative, that's the team that's going to win the tug of war. So this is the Pauling electronegativity scale. It gives a number, an electronegativity value for each element here. And in general, we notice that as we go across a row, that the electronegativity is going to increase. And that's because we have a more positive nucleus, which is more attractive to electrons. As you go down a column, that value generally decreases. And that's because those electrons are being added into energy levels that are much farther from the nucleus. So again, a weaker attraction for electrons. There are a couple of places that don't exactly follow this trend. So like if you look in the middle at the transition metals, we have it going up and going down. That is why we look at the representative elements. Those are the elements in columns 1 and 2 and 3 through 18. These other elements don't perfectly follow the trend, but it is just a trend. We also see that there's no noble gases. There's no column 18 on this electronegativity scale. And that's because noble gases don't need to form bonds because they already have a full octet of stable electrons. So electronegativity is how strongly an atom attracts electrons in a bond. Since noble gases don't form bonds, they're not included on this scale. So using the information in the electronegativity scale and the values for the different types of bonds, we're going to go ahead and complete this chart here. So we'll do the first row together here. We have calcium. Calcium is a metal. And when we look in the electronegativity table, we get that its electronegativity is 1.0. Metals are going to tend to have lower electronegativity because they get to an octet by losing electrons. Next, we have fluorine, and we know its electronegativity is 4.0. Fluorine is a non-metal. So our electronegativity difference here between 4 and 1 is a difference of 3. So based on this electronegativity difference, we would pick the bond type as ionic. So go ahead and pause the video and take some time to work through the rest of this table, and then come back here when you're ready to check your work. Okay, so now we have Ag, which is silver. Silver is a metal. We also have gold, which is a metal, and the electronegativity difference for gold, or the value rather, is 2.4, and we have a difference here of 0.5. But that really doesn't matter. See how M for metallic is already filled in there? We know this is going to be a metallic bond because we have a metal and a metal. My first compound was a metal and a nonmetal, and that was an ionic compound. Next, looking at HCl. So the electronegativity difference here is 0.9. So we would say that that is polar covalent or moderately polar covalent, but it is polar covalent. Next up, we have gold and copper. Again, we don't care what the electronegativity difference is here. We know it's going to be a metallic bond because we have two metals. Next, we have hydrogen and hydrogen. So since these are both the same element, the electronegativity difference is 0. So this is going to give us non-polar covalent. Next, we have Mg, which is a metal, and Cl, which is a nonmetal. Now, when you subtract here, we get 1.8. So you might be tempted to say very polar covalent. But this is actually going to be ionic. Reason being, we have a metal and a nonmetal here. And then we have hydrogen, and oxygen, two nonmetals. My electronegativity difference here is 1.4, so we would predict that this bond would be very polar covalent. So we want to fill in this table to kind of summarize our findings here for these different types of bonds. So go ahead and pause the video and take a couple minutes to summarize your observations about the electronegativity difference and the types of elements involved in these different types of bonds. So ionic compounds are going to have a very large electronegativity difference. This is going to be formed between a metal and a non-metal. For polar and non-polar covalent, polar just means that those electrons are not being shared equally because one of those elements is much more electronegative. So if we have a moderate difference, about 0.4 to 2, and we have two nonmetals, we're going to have a polar covalent bond. A nonpolar covalent bond just has a very small electronegativity difference, but it's still comprised of nonmetals. So if you have a metal and a nonmetal, it's going to be an ionic compound. If you have nonmetals, it's going to be either polar or nonpolar, depending on the electronegativity difference. And lastly, for metallic bonds, the electronegativity difference doesn't matter. We know that it's metallic just because we have two metals forming a bond. So it's really important, we saw in the one example, you don't want to think of this as like a hard division between polar, nonpolar, and ionic. It's more like a continuum. So we see that as we have a greater electronegativity difference, we get a larger distribution of charge. It becomes more like an ionic bond. So when we look at our nonpolar covalent bond, we've got two atoms here, and these black dots are representing electrons. And if you look for nonpolar covalent bond, those electrons are being shared very equally between these two atoms. And that's because they have very similar electronegativity. One isn't more attractive than the other. When you look at a polar covalent bond, we still have sharing going on, but it's not equal sharing. One of these atoms is kind of hogging the electrons here. So that's what makes this polar. And then lastly, we have this ionic bond. So in the ionic bond, we're not sharing electrons. The more electronegative atom has taken the electron away from the other atom. So you should think of an ionic bond as like an extreme version of a polar covalent bond. The difference in electronegativity is so big that one element, one atom, can take the electron away from another. So we had that example in the chart where we had a difference of 1.8. Technically, that was in our polar covalent range. But since we had a metal and nonmetal, we would conclude that it's an ionic bond. Okay, so take a couple of minutes to pause the video and work through question 4. So we're going to find Na and Cl and highlight those. So Na is going to be over here, and Cl is over here. And then we have our carbon and oxygen right here. Okay. So the pair that's going to form an ionic bond here is going to be my metal and my nonmetal. And the reason for that is they are on completely opposite ends of the periodic table. So remember that as you go across the periodic table, that electronegativity increases. So Na and Cl are going to have a big difference in electronegativity, whereas C and O won't have as big of a difference. So the metal and nonmetal will give us our ionic bond, and the two nonmetals will give us our covalent bond. So which pair of elements would we expect to have a larger electronegativity difference? So if you look at the distance between carbon and oxygen versus the distance between sodium and chloride, Sodium and chloride are going to have a big electronegativity difference because they're really far apart on the table. Okay, go ahead and pause the video and take a couple of minutes to work on these questions, and then come back here when you are ready to check your work. So sodium has the electron configuration shown here, and its highest energy level is 3s1. So it has one valence electron, and its electronegativity value is 0.9. Fluorine has a total of 7 valence electrons, and it has a very high electronegativity value of 4.0. So in order to be stable, we want a full octet, 8 valence electrons. So looking at fluorine has 7 valence electrons. It's really close to having an octet. So fluorine is going to be highly attractive to electrons. It has a very high electronegativity value because it wants to gain an electron, not lose any. How many valence electrons would sodium have if it lost this 3s1 electron here, forming the cation Na+? So if we lose that 3s1 electron, we see that the second energy level here has a full octet. So if the 3s1 electron was lost, the highest energy level would then be energy level 2, which does have a full octet, making it more stable. Go ahead and take a couple of minutes to work on your response for Journal Write 3.